Joseph Kishore. Right. Students, can you hear me now? Okay. Hello.
Yes, sir.
Oh,
Audible.
right. Fine. Thank you for bearing me. Uh, See, we have discussed this special problem in the last class. See, today's class, uh, I am going to have a brief overview of what all we have studied. And in the next class, that means tomorrow, we are going to start the second unit. Okay. This class is almost over. I mean, this chapter is almost over. And tomorrow we are going to start the new chapter. Uh, so let us have just a review of what all we have studied. So you may recall that when we started discussing about the single point cutting tools, when I mean by cutting tool, I shall understand that this is nothing but a wedge shaped device. So cutting tool is nothing but a wedge shaped device. That means it is something like a block, but some of the faces have been say ground at an angle so that you have a sharp corner, right? So that I call it as wedge. So cutting tool, when I mean by cutting tool, it is nothing but a wedge shaped device and it removes the material, that means excess material, to obtain the required size, shape, and of course accuracy, right? So you can observe this wedge, whether it is a turning process, shaping process, a drilling process, or a milling process, or whatever be the machining process, including grinding. Okay, when I talk about the cutting tools, so the cutting tools, they may be single point cutting tools, double point cutting tools, or multi point cutting tools. Single point cutting tool, a turning tool, and such similar tools. So when I mean by double point cutting tool, drill bit is nothing but double point cutting tool. When I take up the milling cutter, when I take a hob, when I take up the case of a hacksaw, or even when I take the case of a grinding wheel, so they are all multi-point cutting tools. So when I mean by single point cutting tool, multi-point cutting tool, the number of tool points are going to be multiple in case of multi-point cutting tool. So when we talk about the single point cutting tool versus multi-point cutting tools, we have their relative advantages and limitations. So single point cutting tool, easy to design and fabricate. Fabricate means grind those surfaces. Comparatively cheaper, but you cannot have longer tool life. There is going to be high cutting temperature and there is lesser material removal rate. On the other hand, when I take up this multi-point cutting tool, what all negative points I'm having here, I am going to overcome in case of multi-point cutting tools. Right? When I take up the geometry of single point cutting tools, I have to divide the cutting tool into two parts. One I call it as tool point. Another part I call it as shank. So I have the place over which the chip flows, which I call it as face or rake surface, and the remaining portion where it supports, I call it as shank. The two flanks are relieved so that there is not going to be any rubbing of this surfaces. This is only single. In case of multi-point cutting tools, I have such type of points, tool points, multiple in number in a single tool. Okay. So these are the parts at different levels: volume level, area level, line level, point level, and angular level. So angular level, I call it as clearance angles, cutting edge angles, and rake angles. So when I try to describe what are the angles, I need a particular designation system. I call it as ASA system, ORS system, NRS system, or British maximum rake system. But most of the times, the American Standard Association system, that is ASA system, or orthogonal rake system, these two are very convenient for me to use. So when I take up the ASA system, so I define the angles in 3 planes: reference plane or tool base plane, machine longitudinal pi x plane, machine transverse pi y plane, right? So this is the view what I get in the top view or the tool base plane. So end cutting edge angle, side cutting edge angle. So for the side cutting edge, if I cut it, remove this front portion, see what appears. So this is the pi x plane. So this is parallel to the axis of the machine, right? So ఇక్కడ కనిపించే యాంగిల్స్ ఏంటంటే, so this gamma x and alpha x. Gamma x stand for the rake angle, right? Side rake angle. So this is side clearance angle, sorry, end clearance angle. So likewise we have 2 more angles when I cut in pi y direction. So this is the back rake angle, end clearance angle, sorry, end clearance angle, right? So this is a very convenient method. Many times we use it. So each of the angles have their own implications. They have some function to perform, right? So I write the tool angles in a particular fashion, in a particular order. So that is called as a tool signature, right? Gamma y, gamma x, alpha y, alpha x, phi e, phi s, r. Next, this is the ORS system. When I talk about the ORS system, I have the tool base plane. So phi 1, phi 2 angles are defined. So I look to a plane which contains this side cutting edge, which contains the projection of the side cutting edge anna parallel. So that I call it as phi c, which is called as cutting plane. And the next one, I look perpendicular to the projection of the side cutting edge. So what I get is a picture something like this. So this is nothing but my orthogonal rake angle, orthogonal clearance angle. So this is called as the back rake, lambda, back rake or German back rake, right? So one more angle is defined in another plane, that is the plane which is perpendicular to the projection of this end cutting edge. So auxiliary orthogonal clearance angle, right? So if I put all these angles at one place, I get a signature something like this: lambda, gamma naught, alpha naught dash, phi 1, phi r, right? So based on this, we have done some numerical problems also. We try to verify what is the value given for a particular angle or at a particular place. I look to the numerical value and imagine that, for example, in this place, the angle I find 5 degrees. I shall mean that my orthogonal rake angle is 5 degrees. Lambda I find 0 degrees. I may understand that it is German back rake. It is 0 degrees. That means inclination angle is 0, right? So this was another issue. Okay. So this was what we studied about the tool angles. Then we have discussed about orthogonal and oblique cutting. Students, can you hear me? నేను చెప్తున్నది వినిపిస్తుందా?
Yes, sir.
Okay. So don't be confused. Today, as per the instructions, we are taking a sort of revision class, right? So that
Yes, sir.
all the topics are covered. అంతకుమించి ఇంకేం లేదు. So I mean, I need
Okay,
not
sir.
delay to jump into a next topic. Just we want to have a small revision class. ఈ ఒక్క రోజు మాత్రం revision అనుకున్నాం, right?
Okay, sir.
Talking with other teacher, we are having a small revision class. Okay, right. So when I talk about the next type of cutting process, that is the orthogonal and oblique cutting. So I can have the cutting as orthogonal oblique or oblique. So depending upon its cutting edge velocity relationships. So cutting edge etla undi, how is the velocity vector? So both of them are perpendicular to one another. I call it as orthogonal cutting. On other hand, చూడండి, cutting velocity vector and this is the cutting edge. So ఈ రెండింటికి మధ్యలో ఉన్న యాంగిల్ చూడండి, if it is something other than 90 degrees, 90 ఇక్కడికి వచ్చింది, but my edge is somewhere here, right? So I have got some extra angle or a lesser angle. Either way it can happen. So that is called, actually this is called as the cutting edge inclination angle. So here you may look, so this is the direction of the velocity vector, right? Or perpendicular to the direction of the velocity vector, I have a line. So ఆ లైన్ కటింగ్ ఎడ్జ్ రెండు ప్యారల్ గా ఉన్నాయి అనుకుందాం. So then the cutting is orthogonal cutting. Other hand, I have this line which indicates cutting velocity vector. I draw a perpendicular to the velocity vector. I find a line something like this. Angle between this perpendicular to velocity vector and this main cutting edge, I have an angle. So that is not zero in case of oblique cutting, right? So what is the implication of this inclination angle? ఈ కేసు అయితే inclination angle 0. ఇక్కడైతే some finite value, non-zero value. You can look. The first implication is the cutting forces. You can have only cutting force and thrust force in case of orthogonal cutting. But in oblique cutting, you are going to have cutting force, radial force, thrust force. So cutting force, Pz, the radial force. So the radial force is nothing but my field force. Thrust force is nothing but Py, right? So 3-dimensional cutting, 2-dimensional cutting. Another implication is shear force acts on small area. So 2 life is small. In this case, in oblique cutting, the cutting edge, the shear force is acting over a larger area. Therefore, I can expect better tool life. So cutting edge clearing the width, cutting edge not clearing the width. Flow of the chip perpendicular to the cutting edge, flow of the chip is not perpendicular to the cutting edge. Instead, it is at some angle, which I call it as chip flow angle. So better tool cutting, better tool life, lesser tool life in case of orthogonal cutting. ఇక్కడ తప్పుబడింది. So oblique cutting, the cutting tool has ఇక్కడ better ఉండాలి. I'll make a correction, nothing to worry. So this is a better tool life. So there is a print mistake. So the cutting tool, okay, don't bother. There is what we call a print mistake, which, right, you can understand that the tool life is better in the case of oblique cutting. In addition to this, you may observe that the chip is tightening into a spiral. In the second case, the chip is tightening into a helix, right? So this is an example of orthogonal cutting. So this generalized case, we call it as oblique cutting, right? So this is looking at the metal cutting in some other manner, right? That means orthogonal cutting versus oblique cutting. Just wait. Okay. So another thing of importance which we have to speak is nothing but the mechanism of chip formation. Previously, people used to think that when the cutting tool presses against the workpiece, there is a crack formed ahead of the cutting edge, but this was found to be false. Instead, there is going to be a continuous shearing of the chip over the rake surface, right? So there is no crack formed. So this has been proved to be correct, and this has proved to be it is not correct. That means it was only a misconception. The next thing what you have to observe is chip formation is nothing but a sort of chip formation is nothing but a sort of shearing process. So when I apply a force, you will find that one of the surface will slide with respect to other surface, right? So that is nothing but the shearing action. The same shearing action shall be observed in metal cutting process also. You can imagine whatever the material that is entering, it will simply rotate about the cutting edge when the rake surface over the shear plane. You can find that the line AD rotates and takes a new position AE. Similarly, BC rotates and takes a position BF. So a sort of rotation takes place. So similar to what has happened in this place, this is sort of shearing takes place. So I may conclude that metal cutting is nothing but a sort of shearing process, right? So this is one important phenomena one has to understand. The next thing is I have to observe that there is a sort of compression of the work material. When the cutting tool moves with some velocity Vc, I find that there is a region of separation between the uncut material and the material that has been cut. So that border I call it as shear plane. So the uncut material transforms into chip, right? After passing through that region. So I may understand that the thickness of the uncut material at that place is T1. After it crosses that shear plane, the thickness is T2. So T1 transforms to T2. So I may accept that T2 is always greater than T1, right? So when you look to a shaping process, you may find that T1 is here, thickness, T2 is thickness here. Similarly, length is L1 over here, L2 in this place. You may observe that length is decreasing, however, thickness is reducing. So if I talk about the volume constancy, L1 T1 B1 is equal to L2 T2 B2. So with B1 is equal to B2, which we call it as no side flow condition, I may observe that L1 T1 is equal to L2 T2. Ante the rate of thickening of the chip is equal to the rate of reduction in the length. One I call it as chip thickness ratio. Other I call it as chip reduction coefficient. There is a term known as chip reduction coefficient. Chip thickness ratio వచ్చేటప్పటికి నేనేం రాశాను T1 by T2. So thickness before cutting, thickness after cutting. If I talk about chip reduction coefficient, I write as L1 by L2. L1 by L2 రాశాను అనుకోండి. Length of the chip before cutting, L1. Length of the chip after cutting. That I call it as chip reduction coefficient. The next term which I may speak about is nothing but the shear angle. What is this shear angle? So whenever the chip transforms, I mean the material transforms into chip, there is a transformation taking place about a line or about an area. Many times in high speed cutting, which is often followed, we find that this region is nothing but I mean this almost a plane, right? This region of separation I call it as shear plane, and the angle with which there is a with which the shear plane makes with respect to the velocity vector, ఈ డైరెక్షన్ ఆఫ్ వెలాసిటీ వెక్టర్ ఉంది కదా, ఆ వెలాసిటీ వెక్టర్ తో చేసే యాంగిల్ ని షియర్ ప్లేన్ యాంగిల్ అంటాను. సో ఐ కాల్ దట్ యాంగిల్ యాజ్ షియర్ ప్లేన్ యాంగిల్, which I represent by beta. So this shear plane angle is an important parameter which tells me the nature of cutting, because it's going to affect the chip thickness. If shear angle is smaller, chip thickness will be more. If the shear angle is lesser, if the shear angle is lesser, chip thickness is large. If shear angle is more, then I will find that definitely T2 will be greater than T1, but it's not so high as in a case where shear angle is smaller. You can observe this diagram. You can see the implication. You look to the case. ఈ కేసులో చూసాను అనుకోండి, beta 2 is less than beta 1. Beta 2 is less than beta 1. So ఈ beta 2 చూడండి, it's a smaller value of shear angle compared with beta 1, right? Therefore you are finding more length of the shear plane. So shear plane length పెరిగే కొద్దీ ఏమవుతుంది, the length over which the chip has to bend or slide will increase. Therefore I require more energy. Okay, so this is one important issue. And next thing what you have to talk about here is the shear plane angle. What shall be the value of shear plane angle? So if I look to this diagram, if I do some trigonometry, I may get the value of the shear plane angle beta. If I try to work it out by writing T1 by T2 is equal to chip thickness ratio R, if I try to get the value of beta, the derivation will result in tan beta is equal to R cos gamma by 1 minus R sin gamma. You observe what are the things here. ఈ tan beta ఎట్లా వచ్చింది అంటే it depends upon R. R is nothing but the chip thickness ratio. Then what is this value? It depends upon the rake angle gamma. So rake angle gamma, chip thickness ratio R. These two are going to decide the value of beta. Then who will decide the value of gamma? Who will decide the value of R? Gamma అనేది ఎవరు డిసైడ్ చేస్తారు, మనమే డిసైడ్ చేస్తాం, because we grind the rake surface at a particular rake angle. Then who will decide the value of R? There are so many issues. We shall talk about that in the next instance. Let us go to the next discussion. At an appropriate place, we'll come back to this point. R అనేది ఎవరు డిసైడ్ చేస్తారు, బీటా అనేది ఎవరు డిసైడ్ చేస్తారు, right? So that point again we shall come and discuss. The next type of issues which we have to talk about are the cutting forces. When I talk about cutting forces, we may observe that, just please be online. If I look to the cutting forces in turning operation, so you may observe this is an oblique cutting, or rather you find all the three forces: feed force Px, thrust force Py, cutting force Pz, right? So if I put all these three forces at a single place, Px, Py, Px, Pz, and try to find the resultant. So R is my resultant. So ఇక్కడ ఏంటంటే all three forces కనిపిస్తున్నాయి. I can have cases where one of my Px or Py can be absent. So that depends upon my plan approach angle phi. Plan approach angle phi వచ్చి 90 degrees అయింది అనుకోండి, Py 0 అయిపోతుంది. So I may observe a special type of turning, something like this, which I call it as shoulder turning. ఈ shoulder ఒకటి ఫార్మ్ అవుతుంది, that I call it as shoulder turning. Still I may observe one more type of turning which I call it as radial turning, where phi is 0 degrees. ఈ కేసులో చూడండి, phi is equal to 0 degrees. In this case, Px is equal to 0. Px, the feed force is 0, right? So ఈ రెండు కేసెస్లోనూ స్ట్రైట్ ఫార్వర్డ్ గా ఒకే ఒక పర్టికులర్ Px Py లో రెండిట్లో ఒకే ఒక ఫోర్స్ ఉంది. either Px is 0 or Py is 0. In this case, Py is 0 when phi is equal to 90 degrees or in this case, Px is equal to 0 when phi is equal to 0 degrees, right? Please observe this. So this is some great, what we call, or this should be a good introduction for cutting forces, how to deal with cutting forces. Next, we shall talk about the Merchant's analysis. What is this Merchant's analysis? What does this Merchant's analysis tell? Look here. So the first scientific treatment of the force analysis. What is the meaning of force analysis? So we should be able to try to find out the resultant of forces. Generally, మనం force analysis mechanics ఏం చేస్తూ ఉంటాం? We try to resolve the forces. We try to find the resultant of the forces. We try to see what is going to be the effect of that force, right? Here we find that the effect of the force is just to drive the chip, or in addition to cause a shearing action to take place. So ఈ రెండు actions జరుగుతున్నాయి. If I try to observe this mechanics, I may follow what the two scientists Merchant and Ernst have performed. So these people consider the shearing region as a plane, right? In reality, whether it's a plane or not, it's the next question. So actually, there are two more theories, or rather, not two, simply a few more theories. Lee and Schafer's theory, Oxley's theory, Jarrell's model, ఇవన్నీ పట్టించుకోకర్లేదు. As a student, we can understand this Merchant's analysis very easily. And if this is understood properly, then we can think of other type of complicated theories in your higher studies, right? So when I want to make this Merchant's analysis, I have to make some assumptions. First one, no contact with the flank. Ante clearance angle baga undi. So the cutting edges, the tool is perfectly sharp. So rake angles, cutting edge angles, as well as when I talk about this clearance angles, they have been ground properly that the tool flanks shall not rub with the workpiece. There is no side flow of chips. So B1 is equal to B2. So ఇది ఇప్పుడు మీకు ఇప్పుడు అర్థం కాకపోవచ్చు. There is a condition known as plane strain. Plane strain, plane stress and రెండు conditions ఉన్నాయి, right? Where I may observe strain taking place only in one plane. So you may observe this in some of the higher studies, right? Cutting velocity is uniform. Continuous chip without built-up edges form. There is no chip flow deviation. Okay. So under the action of, with these assumptions, the chip is treated as a rigid body held in equilibrium under the action of these two sets of forces. And when I look to these forces, when I call two sets of forces, one set of forces, the forces transmitted across the chip tool interface, and the other set of forces across the shear plane, right? So chip ila undi. So one set of forces, PS, PN, this will produce one resultant. There is another set of forces, frictional force, normal force. This will produce another resultant. This resultant R and this resultant R dash, both of them are equal, and they will keep this chip in equilibrium, right? I may assume as though some steady process is taking place, as though some static condition is observed. So ఒక static equilibrium లాంటి నేను చూస్తున్నట్టుగా భావించుకోవచ్చు, ఏం తప్పలేదు, right? So Merchant cleverly put all these forces into a single diagram, which he called it as Merchant's circle diagram. చూడండి, అన్ని ఫోర్సెస్ తీసుకొచ్చి ఒక ప్లేస్ లో పెట్టేశారు. Just for a while, forget Px, Y and Pz. Actually Pz and Pxy ఇవి కాసేపు మర్చిపోండి. మనం ఇందాక చూసిన ఈ టూ సెట్స్ ఆఫ్ ఫోర్సెస్ మనకు ఈ డయాగ్రామ్ లో కనిపిస్తాయి. PS, PN, N, F. One of them resultant R, one of them resultant R dash, right? So R dash and R, they are equal. So they keep the chip in equilibrium. Now let me talk about this PZ and PXY. ఈ PZ PXY ఏంటి? So cutting force because of the rotation of the workpiece. Pxy, the resultant of the feed and thrust force. Right? So these two forces in the active forces, the forces which I am applying, these two, they convert into this PS and PN. నేను అప్లై చేసిన ఫోర్సెస్ ఏమవుతున్నాయి, అవి షేరింగ్ జరిగేలా చేస్తున్నాయి. సో దేర్ టూ ఫోర్సెస్ PZ as well as PXY transform into two forces PS and PN. And then when I look to this N and F, these are reactive forces. కట్టింగ్ జరిగింది, చిప్ మూవ్ అవుతుంది. సో మై ఫ్రిక్షన్ ఫోర్స్ ఈస్ నథింగ్ బట్ రియాక్టివ్ ఫోర్స్. యాక్టివ్ ఫోర్స్ ఏంటంటే PS PN, రియాక్టివ్ ఫోర్స్ ఏంటంటే ఫ్రిక్షన్ ఫోర్స్, దానికి కరస్పాండింగ్ గా ఉండే నార్మల్ ఫోర్స్. రైట్? You may observe angle beta shear angle here. I am observing another angle eta, which is nothing but my friction angle. I may observe rake angle gamma. ఇందులో మీరు అప్లై చేసేటివి అవి ఆటోమేటిక్ గా ఫార్మ్ అయ్యేటివి. ఇక్కడ అబ్జర్వ్, గామా is some angle which is coming because of grinding the tool with a particular slope, right? So beta is an angle which is coming on its own. So your beta will decide what is going to be the value of, your beta is going to decide what is going to be the value of shear force and normal force, right? And therefore it will decide what is going to be the value of N as well as F. Of course, when I mean by friction, the surface conditions of the rake surface, the sharpness of the cutting edge, they will decide the value of N and F. If I try to resolve these forces in terms of forces which I know, that is PXY, PZ, ఈ రెండు forces నాకు తెలుసు. In terms of these two forces, if I try to resolve, I am going to get the forces put into a matrix form, NF, cos gamma, sin gamma, cos gamma. So I have a term gamma. చూడండి, cos gamma, sin gamma minus sin gamma. Actual గా ఈ determinant value 1. So if I take this cos square plus sin square, it will go to 1. So NF, PZ to PXY. PZ first రాసాను, PXY next రాసాను. So same matrix system, I put PZ, PXY, instead of gamma I put beta, right? So what is that I am going to get? Check it. I am going to get PS, PN, right? So this is how I am able to easily remember the values of these cutting forces, right? Students, just please wait, don't go away. I may just extend for a few minutes, not so a long time, because we want to have a summary session which shall be recorded properly and that shall be uploaded to the website. Okay, just please stay back. So what this Merchant's theory tells? This Merchant's theory tells that shear angle will automatically adjust itself to such a value that work done in cutting is going to be minimum. The Merchant theory, or these two scientists proposed that the shear angle will take a value in such a way that work done in cutting is minimum. So mathematically I try to obtain what is going to be the work done. So work done is equal to PZ into VC. So cutting force multiplied by cutting velocity, right? If I try to obtain these expressions, I will have to once again go to the Merchant's circle diagram. I'll have to go to this Merchant's circle diagram, right? I shall write PZ in terms of R as well as PS in terms of R. So PS is equal to R cos beta plus eta minus gamma, PZ is equal to R cos eta minus gamma. If I divide by one by another, so I will be eliminating the value, the symbol R. R is eliminated. The resultant force is eliminated. Further, I may write PS is equal to tau S into AS. Tau S stands for the shear strength of the material. That means it is a property of the material. AS is nothing but the area of shear. if I try to observe what is going to be this area of shear, right? ఇలా సెక్షన్ చేసి చూపిస్తున్నాను చూడండి. So that is nothing but my area of shear. This area of shear, it is T3 into B2. That is equal to T1 into B1 by sin beta. So thickness of the chip before cutting, width of the chip before cutting. So T1 B1 by sin beta, right? So if I simplify this, I will get an expression for work done as tau s T1 B1 VC cos eta minus gamma sin beta cos beta plus eta minus gamma. Now I will differentiate this expression for work with respect to beta, dou W by dou beta. So ఇక్కడ ఉన్న టర్మ్స్ లో టిఎస్ T1 B1 VC ఇవన్నీ కూడాను they're constant with respect to beta. సో ఇవన్నీ పోతాయి, ఇంకా మిగిలేది టర్మ్స్ ఏదంటే ఈ రెండు మాత్రమే మిగులుతాయి. So if I perform that differentiation, what is that I am going to get is a condition tan pi by 2 minus beta is equal to tan beta plus eta minus gamma. Tan pi by 2 minus beta is equal to tan beta plus eta minus gamma. So 2 beta plus eta minus gamma is equal to pi by 2 is the final expression which I shall obtain. So this is called as shear angle solution of Merchant's and popularly known as Merchant's first solution, right? So this type of solutions are called as shear angle solutions. ఇందాక మనం అనుకున్నాం చూడండి, షియర్ యాంగిల్ ఎంత అవ్వచ్చు అనేది. వాట్ విల్ బి ద వాల్యూ ఆఫ్ షియర్ యాంగిల్ అంటే tan బీటా అన్నాను చూడండి, tan బీటా ఈజ్ ఈక్వల్ టు r cos gamma by 1 minus r sin gamma అన్నాను, బాగుంది. When I keep in mind the condition that work done in cutting is going to be minimum, I shall get the value of beta as this much, pi by 4 gamma by 2 eta by 2. Gamma అంటే ఏది? Gamma is nothing but my rake angle. Eta is what? F by tan eta is equal to F by n. So it is something which is related to friction coefficient. So rake angle, friction coefficient. These two will decide what is going to be the value of beta. Then beta will decide what is going to be the value of chip thickness ratio R. Right? So this is how things happen. I repeat, when I look to the value of beta, I find that it is going to depend upon the value of this is not R, this is gamma, please. R gamma ఒకటేలా కనిపిస్తుండొచ్చు మనకి. So this is the value of gamma. This is gamma, this is eta. So when I talk about gamma, which is nothing but the rake angle, it's the condition of the rake surface. Eta, it will tell what is the friction condition. Your rake surface condition, friction condition together will decide the value of beta. When I know the value of beta, tan beta is equal to r cos gamma by 1 minus r sin gamma and Raschel. So when I fix up the value of beta, my chip thickness ratio is going to depend upon the value of beta. So are you able to understand what I am telling? మీరు కరెక్ట్ గా అర్థం చేసుకుంటే this is most or critical or very crucial what we call point where one will understand the metal cutting properly. Shear angle ఎంత వస్తుంది అంటే it is going to depend upon the value of gamma and eta. That means rake surface condition, that means rake angle, and friction condition eta. When I know the value of beta, I will be able to tell what is going to be the value of R. నేను యాక్చువల్గా tan beta is equal to r cos gamma by 1 minus r sin gamma రాశాను, కానీ who will decide the value of chip thickness ratio? Tan beta will decide the value of chip thickness ratio R. Gamma is nothing but the property of the material. I mean property of the geometry. So gamma fix అయిపోయింది. ఇక నాకు బీటా తెలిస్తే ఆర్ తెలుస్తుంది అని అర్థం, లేదా వాళ్ళు ఆర్ ఉంది అంటే బీటా కనుక్కోవచ్చు అని అర్థం. బట్ ఇన్ రియాలిటీ యువర్ బీటా విల్ డిసైడ్ ద వాల్యూ ఆఫ్ chip thickness ratio R. Right? Next, when I try to understand what is the accuracy of this solution, this shear angle solution beta is equal to pi by 4 plus gamma by 2 minus eta by 2. This first angle solution had some difficulties. So it is perfectly agreeing with synthetic plastics. Synthetic plastics cut చేసినప్పుడు పర్లేదు, లేనప్పుడు స్టీల్ అట్లాంటి వాటికైతే కొంచెం డీవియేషన్, స్మాల్ అమౌంట్ ఆఫ్ డీవియేషన్ ఇస్ అబ్జర్వ్డ్. So it is beyond the scope of my syllabus to discuss about the second solution, which we call it as Merchant's second solution. ఇంకో సందర్భంలో కావాలంటే ఎప్పుడైనా మాట్లాడుకుందాం Merchant's సెకండ్ సొల్యూషన్. ఏం లేదు, ఇక్కడ Merchant's ఫస్ట్ సొల్యూషన్ సెకండ్ సొల్యూషన్ తేడా ఏమొస్తుందంటే it is nothing but the tau s. So when I talk about the forces, I will tell the property of the material is going to depend on beta. అట్లా అన్నాను అనుకోండి, కండిషన్ మారిపోతుంది, ఇంకేం లేదు. ఇన్ దట్ కేస్ ఐ పుట్ ఎ టర్మ్ నోన్ యాజ్ కే. కే అని ఒక టర్మ్ ఈ సొల్యూషన్ లో పెట్టేస్తున్నాను. ఓకే, ఇన్ సమ్ అదర్ సిచ్యువేషన్ వి షల్ డిస్కస్ అబౌట్ దిస్, రైట్? సో దిస్ మర్చెంట్స్ అనాలిసిస్ ఇస్ ఏ ఇంపార్టెంట్ అనాలిసిస్ which is performed on metal cutting. So out of this merchants analysis, what is that you gain, or what is that you obtain by understanding this properly? It is possible to predict the value of shear angle, and then it is possible to know what is going to be the work done in cutting. That means it is possible to know what should be the rating of the motor which is necessary to drive the job so that metal cutting is performed, right? So in this context, we have done some numerical problems, and we have also discussed about the types of chips. Since this is a summary class, let me tell about the types of chips also, then we'll conclude. Look here. Okay. Just a second. Okay. So when I talk about the types of chips, there are different ways of classifying the chips. One way of classifying the chips is looking to the shape of the chip. It may be ribbon, tubular, spiral, washer, coil, helix, arc, element, needle. Again, the chips may be long, shorter, snarled, అంటే చుక్కుపడినట్లు ఉన్నాడు, right? But the way of looking at the chips is generally in some other manner. So I call it as continuous chips, discontinuous chips with built-up edge, right? When I mean by continuous chip, I find a ribbon type of chip. అంటే అలా లాగేస్తుంటే ఒక షీట్ ఆఫ్ పేపర్ లేదా ఒక స్ట్రిప్ అలా బయటకు వచ్చేస్తున్నట్టు ఉంటుంది. సో దట్ ఈస్ నోన్ యాజ్ ఎ కేస్ ఆఫ్ కంటిన్యూస్ చిప్. సో వెన్ ఐ హ్యావ్ ఎ కంటిన్యూస్ చిప్, ఇక్కడ అలా కొన్ని గీతలు లాంటి ఘాట్లు లాంటివి పడుతూ ఉంటాయి, రైట్? సో ఇట్ ఈస్ అబ్జర్వ్డ్ ఇన్ దట్ మ్యానర్, రైట్? లోయర్ సైడ్ చూసానంటే షైనీ సర్ఫేస్ ఉంటుంది, స్మూత్ షైనీ సర్ఫేస్, రైట్? సో పై సైడ్ అంతా నాచెస్ కనిపిస్తూ ఉంటాయి, కింద సైడ్ ఏమో షైనీ సర్ఫేస్ కనిపిస్తూ ఉంటుంది. సో సచ్ ఎ టైప్ ఆఫ్ చిప్ ఈస్ కాల్డ్ as continuous chip. The continuous chip is mostly preferred. The continuous chip is mostly preferred on account of the least amount of force required to perform cutting, and therefore it will give better tool life, right? So conditions under which this type of chip is formed is ductile materials, fine feed, high cutting speed, large rake angle, sharp cutting edge, smooth tool surface or rake surface, and best lubrication system, right? Under such conditions, I am going to get a continuous chip. There is another situation where I get discontinuous chips. When I get discontinuous chips, the meaning is I get fragments of chips. చిన్న చిన్న ముక్కల్లాగా వచ్చేస్తుంటాయి. There shall not be any ribbon type of chip formation. So such type of chips are called as discontinuous chips. So it can mainly seen in brittle materials like cast iron, bronze, right? You may observe that discontinuous అన్నా కూడా జస్ట్ అలా నేరుగా ముక్కలుగా విరిగిపోదు. There is some amount of plastic deformation also. If I look to it closely, I will find that over this plane of separation, there is going to be a extrusion. ఇది కరెక్ట్గా చెప్పాలంటే ఇది ఒక రకమైన ఎక్స్ట్రూషన్ లాంటిది. సో దిస్ ఎక్స్ట్రూషన్ రిజల్ట్స్ ఇన్ ఏ గ్రోత్ ఆఫ్ హంప్ అంటే ఒక బుడగలాగా పైకి పెరుగుతూ ఉంటుంది, రైట్? సో దట్ హంప్ when it grows to a particular size or a tolerable size, it will break away, right? It will rupture away from the remaining material, and this is nothing but my chip. So ila chips mukkalga vastu untai, right? So that is nothing but a sort of discontinuous chip. Okay. Conditions favorable: brittle materials, greater depth of cut, low speed, small rake angle. See the fun. Ductile materials also can give discontinuous chips under conditions of low speed. కటింగ్ స్పీడ్ కనుక తక్కువ ఉంది అంటే డక్టైల్ మెటీరియల్స్ కూడా డిస్కంటిన్యూస్ చిప్స్ ఇచ్చేదానికి ఛాన్స్ ఉంది, రైట్? అండ్ స్టిల్ దర్ ఇస్ అ థర్డ్ టైప్ ఆఫ్ చిప్ విచ్ వి కాల్ ఇట్ యాస్ కంటిన్యూస్ చిప్ విత్ built up edge. So this is a worst type of chip. This worst type of chip, how it will occur? First, let us to look to the conditions under which they will occur. Then we shall talk about what is the nature of this chip. Rough rake surface, అంటే there is so much of rubbing. Blunt cutting edge, అంటే కటింగ్ ఎడ్జ్ పదునుగా లేదు, కట్ చేయడం కంటే కూడా రబ్ చేయడము, తర్వాత గట్టిగా నొక్కడం లాంటివి జరుగుతుంటుంది. కోర్స్ ఫీడ్, అంటే ఫీడ్ రేట్ ఎక్కువ ఇచ్చేసాను. లార్జ్ డెప్త్ ఆఫ్ కట్, లో రేక్ యాంగిల్, సో absence ఆఫ్ కటింగ్ ఫ్లూయిడ్, రైట్? ఇన్ఎఫిషియంట్ కటింగ్ ఫ్లూయిడ్. సో ఇవన్నీ ఏం చేస్తాయి అంటే దే ఆర్ గోయింగ్ టు ఇంక్రీజ్ ది టెంపరేచర్ ఇన్ ద కటింగ్ రీజన్. చూడండి, చిప్ థిక్నెస్ చాలా ఎక్కువ ఉంది, థిక్ చిప్. సో వాట్ ఇట్ విల్ డూ, ఇట్ విల్ అప్లై సో మచ్ ఆఫ్ ప్రెషర్ ఆన్ ది రేక్ సర్ఫేస్. సో రబ్బింగ్ ఈస్ దేర్, సో మచ్ ఆఫ్ హీట్ జనరేటెడ్. సో ఇవన్నీ ఏం చేస్తాయి, సమ్ ఆఫ్ ది చిప్ మెటీరియల్ విల్ స్టిక్ ఆర్ గెట్ వెల్డెడ్ టు ది rake surface of the workpiece. So that we call it as built up edge, BUE. ఏమంటారు నేను, formation of built up edge, BUE. So there is such formation. ఓకే, ఇక్కడ చూడండి, ఇక్కడికి వచ్చేటప్పుడు ఏమైంది చూడండి, గ్రోత్ ఆఫ్ BUE. ఏదో కొంత మీటర్ వెళ్ళయింది కదా, పోతే పోన్లే అనుకోవడానికి లేదు. ఆఫ్టర్ పీరియడ్ ఆఫ్ టైమ్ యూ మే ఫైండ్ మోర్ అండ్ మోర్ మెటీరియల్ విల్ స్టార్ట్ అక్యూములేటింగ్. ఇట్ విల్ స్టార్ట్ అక్యూములేటింగ్ ఆన్ ది workpiece, I mean the cutting tool. So that is called built up edge formation or growth of the built up edge. ఈ built up edge పెరిగి ఇన్ఫినిట్ గా పెరిగిపోతూ ఉండదు at some point of time. So this is not going to be staying there because the force on this built up edge will become larger and larger as it grows larger and larger, and therefore it breaks away. It is unstable, and when it breaks away, it will damage some portion of my cutting tool also. కటింగ్ టూల్ మీద ఉన్న వాల్యుబుల్ మెటీరియల్ అంతా లాక్ వెళ్ళిపోతుంది, రైట్? సిమిలర్లీ ద సర్ఫేస్ విచ్ ఇస్ కట్, సో దట్ ఈస్ ఆల్సో గోయింగ్ టు అపియర్. సో బిల్ట్ అప్ ఎడ్జ్ ఫార్మేషన్ ఆర్ బిల్ట్ అప్ ఎడ్జ్ చిప్ ఫార్మేషన్ ఈస్ లీస్ట్ ప్రిఫర్డ్ అండ్ షెల్ నాట్ బి ప్రిఫర్డ్ ఫార్ ది లైఫ్ ఆఫ్ ది కటింగ్ టూల్ ఆర్ ఫార్ ది ఫినిష్ ఆఫ్ ది వర్క్ పీస్ ఆర్ ది క్వాలిటీ ఆఫ్ ది కటింగ్. క్వాలిటీ ఆఫ్ కటింగ్ కోసం చూశాను అంటే కంటిన్యూస్ చిప్ విత్ బిల్ట్ అప్ ఎడ్జ్ ఈస్ never preferred. It's not going to be preferred into, right? It is most undesirable, right? So this is these are the details regarding the types of chips. Actually I have to discuss regarding the chip breakers. Idu okati miss ayindi manaki. Soon I'll post it into your chat box and then we'll talk about it for a few minutes later. Just I may mention that కంటిన్యూస్ చిప్స్ మంచిదే కటింగ్ ఫోర్స్ పాయింట్ ఆఫ్ వ్యూలో, బట్ దెర్ ఆర్ సమ్ ట్రబుల్స్ విత్ కంటిన్యూస్ చిప్ ఆల్సో. కంటిన్యూస్ చిప్ అలా వస్తుంది అనుకోండి, ఏమవుతుంది, ద ట్రబుల్ ఇస్ ఇట్ విల్ ట్రై టు ఎంటాంగల్, అంటే చుట్టుకుంటుంది. ఇట్ ఈస్ గోయింగ్ టు ట్విస్ట్ అరౌండ్ ది వర్క్ ప్లేస్, ఇట్ ఈస్ గోయింగ్ టు ట్విస్ట్ అరౌండ్ ది cutting tool. Therefore what will happen, you may find that this continuous chip will break suddenly. It will fall on the human being who is operating and is going to interfere with cutting. సో ఆ ఇంటర్ఫియరెన్స్ అన్ని అవాయిడ్ చేయాలంటే చిప్స్ కూడా ఒక లెంత్ వచ్చిన తర్వాత ఇంకా చాలే అనుకుని బ్రేక్ చేసేయాలి. సో దట్ మీన్స్ ఆఫ్ బ్రేకింగ్ ఐ కాల్ ఇట్ యాజ్ chip breaker, right? Just so that is the basic function of a chip breaker, right? And let us look to one numerical problem also. So meeku oka typical problem chupichanu last class lo. So a case where just a second, it's not open. Just 1 or 2 minutes I'm going to close down, just bear with me. I'm not finding it here. So did you check the Google Classroom చూసుకున్నారా మీరందరూ? Students,
Yes, sir.
school class లో మీకు కనిపించిందా?
Yes, sir.
Did you see what has happened
Yes,
with
sir.
the problem which I have provided? Huh? Okay, just a
Yes,
minute.
sir.
Okay, at some other place. I'm not able to track it. Just a second. That's a very typical problem. Actually, I have uploaded it, but I'm not finding it in my database. Problems. Right. I find it here. Okay. So, do you remember what I have done in this case? Chudandi. This is ORS tool. A tool with orthogonal rake system. Just I'll mention and I will very soon exit. So, ఈ ప్రాబ్లం మీకు గుర్తుండొచ్చును. I have to identify what are the important angles. ఇక్కడ చూడండి, జీరో ఏముంది ఇక్కడ? Inclination angle or German back rake 0, right? 5 degrees is nothing but my orthogonal rake angle. 75 degrees is my angle, plan approach angle, right? So there, once I identified it like this, I have come to a decision that Px, Py, one of them is 0 general ga aithe. But in this case, since phi is not 90 or 0, I find Px as well as Py, both of them exist. And therefore, I have found out the value of Py, thrust force, as well as the resultant of this thrust and field force, Pxy, right? So this was one issue. Another thing what I try to obtain is the relation or connection between the feed chip thickness. Chudandi, feed is related to chip thickness. Depth of cut is related to width of cut. See the fun. You can find that my derivation has resulted in a formula B is equal to D sin phi. My relationship has resulted in a formula B is equal to D sin phi, D by sin phi. At a width of the chip is equal to depth of cut divided by sin phi. Likewise, my chip thickness before cutting is connected to feed F. T1 is equal to F sin phi. ఈ రెండు చాలా important because when we make the calculations for material removal rate, this is going to greatly influence these things. ఎట్లాగా అంటే, just look. I think I have to go for a different page. You look here. చిప్ ఎలా వస్తుంది చూడండి, ఇలా వచ్చి ఇలా బెండ్ అయ్యి పక్కకు వస్తుంది, రైట్? సో దిస్ ఇస్ నథింగ్ బట్ మై ఫీడ్. నేను ఇలా తిరిగేటప్పటికి ఏమైంది, ఆ మెటీరియల్ మళ్ళీ నాకు ఇక్కడికి వస్తుంది. ఇఫ్ ఐ లుక్ టు ద సైడ్ వైస్, what I'm going to get is nothing but depth of cut in one direction and in another direction it is feed. So ఈ రెండు నేరుగా మన న్యూమరికల్ వాల్యూస్ ని ఎఫెక్ట్ చేస్తాయి. D is equal to D by sin phi, T is equal to F sin phi. So phi is equal to 90 degrees అన్నాను అనుకోండి, B is equal to D అయింది, T is equal to F అయింది. If I tell phi is equal to 0 degrees, what will happen? Mathematically this will go to infinity, but T1, what will happen to T1? It will, you observe that it is 0, but that is not true. అందుకని దీనికి మాత్రం, ఈ కేసుకి మాత్రం 5 other than 0, 90కి అప్లై చేయాల్సి ఉంటుంది. We have also seen the velocity relationships in cutting. So this is the cutting velocity, chip flow velocity, shear velocity. ఈ మూడింటిని రిలేషన్షిప్స్ ఎట్లా తెప్పించాము? We have applied the sine rule. VC by sin theta, VC divided by sin theta is equal to VF by sin beta is equal to VS by sin 90 minus gamma, right? So VF is equal to VC into R, VS is equal to VC cos gamma by cos beta minus gamma, right? So ఈ రిలేషన్స్ ఇవన్నీ maximum information provide చేశాను. So we have also seen specific energy in friction. So work done to overcome friction by volume of material removed in unit time, which we call it as material removal rate, right? So work done వచ్చేటప్పటికి, so work done to overcome friction, that is nothing but friction force into chip flow velocity Vf, right? So we have performed this calculation. I have finally obtained this answer. మీకు ఆ రోజు ఆన్సర్ వచ్చిందో లేదో I don't remember. It has come to be 1.42 watts per mm cube per second, right? So this is one more outcome of what we have learned. Okay, so you have any questions, you can ask me. You have any questions, you can ask me. So there was some delay in my start in the class on account. This is due to some network problem. Okay. So please excuse me. So in the next class, that means tomorrow, we shall start the second chapter, right? So first chapter okate kastamaindi, most tough or rather where you have to put your mind. Now it is down the slope. Inkanni ala easy ga theoretical part ekku untundi manaki. But wherever whatever it is, I advise you to practice the diagrams. And once again, I remember you, I rather remind you to submit the assignments very soon. So how many of you have submitted? I find very few of you submitted. Assignment for Arshad has submitted, Inka submit chesaru. Anybody else who has submitted? Girish. 47 Girish submit chesaru Inka. Others also, meeku unna ee 2 days undi kada malli chesi raseyandi. Nagarjuna has submitted. Fine. Okay. All of you make an entry of your roll numbers into the chat box very soon. I may stop my recording session. Just a second. See, my recording, if it comes to some other students drive, please మీరు దయచేసి నాకు ఒకసారి వెనక్కి పంపించాల్సి వస్తుంది. Okay. I'll stop recording. I'll know who is going to whom it is going into the recording. I'll make a mention. Oh, it is going to Venkatramana sir's drive. Okay, I'll ask him. Nothing to worry.